Okay, welcome back everyone. Let's continue. We start working with this idea of using neural networks to identify images, numbers, and we finished with a model that was pretty bad. And we need to review what happened, right? Moreover, the most important thing is how to solve that problem and how to improve our model to something that makes sense. What do we need to do? Anyway, before that, quick announcements. Number one, according with this, next week is the career fair, and it's a virtual event for grad students. I am assuming that you are going to be there, and I just want to ask if that is the case, because if that is the case, my plan is I do not want to be here alone or with you in the computer doing other things. So unless you tell me a different story, my plan is that we do not have a lecture February 15 because the career fair is morning until 4 p.m. That is the case?
Yes.
Okay, so I am going to post an announcement, but for the people here, no lecture February 15. See you in a week after today. Make sense? Okay, second, also they told me that February 24, the school is doing an event like a picnic for you with professors. So the picnic of the event happened during the morning, and what they are going to do, what we are going to do is the event is 11:30. So if you do not have another class before mine, you can go to the event and then come back and we continue with the lecture. If you have another class before this one, the agreement was that your instructor in the previous class is going to allow you to leave early, and I am going to allow you to arrive late. So you're going to have kind of this period of time for go for the lunch and say hi to everyone and then come back to the lecture. So for February 24, I am going to start the lecture 12:15. So I am going to give you 15 minutes. So you are out in the picnic. Good. So no lecture February 15, and February 24, we start 15 minutes late. Good. Okay, moving forward. What we did before, we're working with this idea of the identification of those numbers. You have the full description. We create a model. This was our model. We described how many inputs, how many outputs, but basically, other than that, we didn't move anything from here compared with the program that we have recognizing the XOR operator, right? And just by doing that, we get results. These results, an opportunity for you to review the confusion metric and the accuracy, precision, recall, and F1 score. And something that I asked you to, at the end of the previous lecture was, this is good or bad? And you told me bad. Well, more specifically, hopefully you agree, this is really, really, really bad. Good. Next, what is the problem? What could be the problem? I mentioned in the previous lecture quickly. Today I am going to go deep. What could be the problem here? The elements that we do not modify. What could be the problem here? There is very few things that could be a problem. Something that I mentioned in the previous lecture at the end and in the continuation today is my problem there can start with the sigmoid function, and my problem there continue with my error. Something that I mentioned to you in the previous lecture, why these things are a problem, why they work perfectly with the XOR, why now we have problems. The explanation in general is this example, this function, everything that we did with the XOR, what we are trying to predict were values, 0 or 1, but as a value. The problem now is that we are using exactly the same elements, this, that we used to predict values. But now, what we are trying to predict is not a value. What we're trying to predict is a probability. And do we get the difference? Among other things, a big difference is that before, here, one output or the other can be calculated in an independent way. But now, one output or the other, or the other, or the other, or the other, they are connected. Because if I select a 1 or a 2, I am also telling that it's not the others. Moreover, I am not doing a calculation for the number. This is not about an equation like the XOR. This is about probability. What is the probability of this picture to be this or that or that? When you move from one scenario in which you are trying to calculate something, a particular value, to another scenario in which you are playing to can be this or that, one class or more classes, what you need to do is to change your equations, because there are going to be equations that work well with probabilities, and you cannot use those for values. And there are going to be equations that work well for values, but you do not use those for probabilities. A simple thing. This guy is very good. It's your fifth choice to calculate the error between one value and another value, because it's the distance between those values, right? That is the concept. What happens when you have probabilities? When you have probabilities in statistics, there are other ways to calculate that. And I am going to talk about it. Makes sense? Okay, that is just the beginning. There are going to be more things, but starting with this. Model number 2, trying to improve what we have. I am not doing anything with the other source code. The only thing that I am doing is the thing that I put in white rectangles. It's the only thing that I changed. Did you notice what I did? Did you notice what I changed? It's in the white rectangles. Let's see. I am still working with this neural network that have the input, the output, and one layer in the middle. I haven't changed that. What is the replacement of the sigma in my example now? What? The sigma, the one in the middle layer, this one. And what is the replacement for the MSE? SAS. A very big name. What is that? Software. The only thing that I did is a new activation for the output, a new activation for the middle layer. I need to explain what they are, but basically my point is they are replacing the sigma that I had before as a standard. I am replacing the error function. It is no longer the MSI. Now I am using something like what? Good news. The only thing that I need to know is the name and why I need to use it. But the implementation is a method that already exists in the library. So it's not like you are going to need to understand this to program this, right? Would be a good idea, not for here. Did you notice other things that I changed at the top? Do you remember what was the value there in the previous example?
Yes.
For the XOR, in my original model, there was a uniform there. Uniform what? Can you help me to remember uniform what? The initial values of the W's, right? What was the meaning of uniform from the initial values of the W? All the W's start with the same value, right? All of them constant. Remember that was kind of one way to initialize the W's? There are others. Initialize all the values of the W's with a constant value is usually not the best idea. But we did it and worked. Let's change that and see what happened. Uniform, not anymore. I put something else. And I am sure that you're thinking like, okay, what is the meaning of all those names there? In terms of the model, you can just replace those things in white, compile and run and see results. I am going to show you the results. But before checking the results, let's talk about the meaning. Number one, for the initialization, I changed the initialization from uniform to this. What is the meaning? Well, option number one, all the initial values for the W was exactly the same. Option number two, let's use random numbers for the values of the W's. Remember that that was an idea that we already had before. Random numbers. Help me. Do you remember that basically we initialize the W's and the values are there used as the first step to start doing calculations, the derivatives? What could be better? To have all the W's in a constant value like 0, or to put values in the W's with random numbers? What could be better and why?
With random, there's more uncertainty. You're not sure if you're going to pick a number totally antagonistic to the real weight.
Yes. Think about this. I am a variable and you are searching for my value. And you are doing that for every single W. What if I start with the value 0? Option number one, that my final value is 0.5 and I start with 0 and it's kind of close, was a good choice. What if you start with the initial value 100, but my value is 0.5? You start very far. So when you select one number, it's like, could be close, could be far, we don't care. What happens when you use random numbers? Random numbers is going to give you the possibility that, yes, maybe for this W here, it's going to be a very bad choice, but who knows? Maybe for this W here, it's going to be a perfect choice. Are we sure that it's going to be better? Not really. It's just, I do not know the value. So instead of using the same for everyone, let's put random numbers. I do not want to grade your final exams. I can give all of you A's. You're going to be happy. However, I am not sure if everyone deserves the A. Probably there are going to be people that deserve the A, but there are going to be people that should have B or C or D. But I am giving the A. A better option, believe me, is random grades. Because random grades, instead of having only usually 5 or 7 8s in the classroom, and for everyone else, I make a mistake. Random. Maybe I guess one of the A's, but also maybe I guess one of the B's or C's or D's. I am going to have a revolution, but as initial value works, random is better. Now, next step. Random is good, but even better if you can have a random and you can be sure that two things happen. Number one, what if you can tell me that all these random numbers have as a mean 0? I want you to create random numbers from 1 to -1. What is a mean equals 0 telling you for those random numbers? Can you agree that if I ask you for numbers, -1 to 1, randomly, and then I do the average can be a negative number, or can be a positive number, or can be 0. If the average is a negative number, that means that most of you think about negative numbers. If the average is a positive number, that means that most of you think about positive numbers. What is this restriction telling me that the mean should be 0?
Equal opportunity.
A balanced number in the values between zeros and ones. If you think in a space, the same or a similar number of distance between this point and the values here and there, balance. So for the W's, instead of all the W's the same, give me random numbers for the W's. However, be sure that the average of those random numbers is 0. That means that I have W's initialized with negative and W's initialized as positive in this -1 to 1, more or less the same number of W's. Why? Because I do not want to have all the W's negative. I do not want to have all the W's positive. That is the reason because I remove the uniform, right? Balance. Second, variance. If you have multiple layers, we only have one so far, but if you have multiple of them, the same variance. Variance statistics. Tell me, what is that? Because the mean is easy, right? The average, okay, whatever. The variance. Usually my question for you, the answer, just in case you do not answer with me. Can you agree with me that this is kind of a simplistic definition of the variance? You have multiple layers. In all of them, I am asking you that the average, the number of positive and negative W's that you initialize is more or less similar because the average is 0. But moreover, I am asking you to calculate the variance, and the variance should be the same across the layers. The distance between this 0, that is the mean, and values in this layer should be in the other layers when you create more than one. In your example, in the things that we're solving right now, this second part do not apply. We have basically one layer. The output is very trivial. For 10 nodes, the variance is not going to be a big deal. But the main thing that we are doing in the next solution of the model that we created before by selecting this one instead of uniform is that now, instead of one constant, whatever that was, now we have positive and negative values, and they are more or less balanced. A different way to start with the backpropagation. Cliff? Really? It's going to make a difference just because you change the initial value? I don't know. We need to review. Good? Yes.
Why do we need to follow the second point?
The what?
Why do we need to follow the second point?
Which second point?
Variance should be the same across layers.
Most of these things are recommendations. Most of these things is keep kind of a constant movement between one layer and the others, assuming that you have more than one. Something that we need to review is that basically when you have more than one layer, it's better to move to convolutional neural network instead of the multi-layer one. One layer is going to solve most of the problems. Adding more layers is not going to make a big difference in most of the problems. But the recommendation, and several things that I am going to mention, these recommendations, is like take care of the average, take care of the mean, and also take care of the same variance between different columns. That's it. I am going to show you what happened when you do not follow that, and you're going to notice there are changes for some of the models. Some of the changes are use 0.0 something. Next, we did this. What could go wrong? Sigmoid. It is easy to explain this with a picture. Do you remember that this guy is the sigmoid type? Do we remember that what we are doing is basically this W with one input plus the W with the other input plus the W with another input? And this is really the equation that I have in a neural net. These additions of W's multiplied with the input. And to all of that, we apply the function. And the only reason, because we apply the function, is to make this plain thing. With the sigmoid, what we do is, okay, very small numbers and very high numbers are going to be kind of flattening thing, and the change is going to be here with the middle ones. With these numbers that are kind of unsure what is going to happen, these ones are going to move or move. I am going to try to separate them, to discriminate them. The sigmoid is very good with values. Values close to 0, close to 1, and in the middle, this S part. What do you think about this one? Is our new guy. Fancy name. It's going to transform the input in a line. The line, yeah, small values, forget about them. Okay, positive values, a line. Small values, big values. There is a full description of why this is important, but the conclusion for the layers in the middle, in a big number of problems, including the one that we're solving, this guy works better. Take in consideration these values, not these values. When this equation, the addition of all these things, go below 0, forget about it. Basically, what you are doing, replacing this with the new one, is forget about these negative values. And let's keep the positive ones. Let's keep this equation when we're putting together the inputs and the W's. The ones that are going to be there are the positive, and moreover, the positive in a linear consideration. I am not going to change or increase or decrease. I am going to keep exactly what I am getting for the layers in the middle. This one in particular, the sigmoid we used before for the output and for the middle. This one, the recommendation, use that in the middle. Do not use that in the output. Crazy things are going to happen when you put this in the output. Again, it depends on your problem. But in general, and moreover for us, this in the middle. Why not in the output? Because our output is a probability. And we do not want to play in this way with probabilities because we have better choices. I am going to show you. More or less? So are you telling me that instead of starting with the sigmoid in the middle layers, it could be a better idea to start, if I do not have more information, with this one? Yes. Start your first draft with this one, not with the sigmoid in the middle. You can start with the sigmoid for the output if you want, unless more information, like the one that we have right now, probabilities. That is giving me a hint about what to use in the output. Make sense? Easy. Okay. Next, this one. Two things are going to happen with that. Two things, yeah. What is going to happen with the output? You know what? If you are going to play with probabilities, when you play with probabilities, you want to use as an activation function in the output this one and this one work together with this for the error. Are you mentioned two equations? Yes, and I am telling you, they usually work together. They are friends. And if you use one, it is a good idea to use the other because they are going to complement each other. What exactly are you telling me that is going to happen here? The first thing that is going to happen is for the output. In the output, do you remember that you have 10 nodes? For those 10 nodes, the activation function here is not going to be sigma. It's not going to be the one that I showed you before, linear, for this guy. And what is going to happen? Very simple. What is going to happen is the equation is kind of this. Just showing you the example. The equation is going to do the following. It's going to do something, an exponent with whatever is the result. The result is this result, the equation that you have. With this result, I am going to do this. I am going to use the output of the function as an exponent. Nothing is going to happen. You're going to get a number. The number is a small number, a decimal number. The important thing is I am going to do this for all the nodes in my output. In each node, I am going to have this at the top of a division. And in the bottom, I am going to have this. Do we understand what is this? You have 10 nodes. For each node, you are going to take this letter and you're going to use this number as an exponent for the letter. For give you an example. You calculate 10. And then you go to the first one, and that number divided by the addition of all. For the second one, that number divided by the addition of the others. So it's me divided by the universe. What is going to happen with that kind of equation? What is going to happen when you calculate, okay, this equation, and now that one is the exponent, but then I divide by the addition of the others. Did you notice what is different here compared with the MSE? Because obviously this is used to calculate the Y, the output, and that is the one that I am going to compare with the real one. One, you are taking into consideration to calculate one output, the values in the other outputs. And the value that you are giving me as a result is not only a calculation that you did for this node, but this one in comparison with this ratio with the total in the others. And you know what happened with that? You are moving from calculating a value to probabilities. Why? Because the addition of all of them is your universe. And when you divide this one, me, with all of them, with the others, is kind of my place in the output. My result is not longer just the equation that I have, but it's that equation, the number that I get, somehow compared to or balanced with the numbers that others get. And that's it. Yes, that's it. This is going to give you an output, and this guy is called softmax, because you're going to use that to compare with the output. Probabilities instead of distance. Okay, good. What about the calculation of the error? Because, okay, this one was to calculate the trigger, the activation function of the neuron. But then we need to do the calculation of the error. Before, with the sig mode, or even with the linear one, the calculation of the error is this one minus this one and the division, right? Now, what is going to happen if I use this one, softmax, here? This result is a probability, and in order to calculate the error, what I am going to use instead of the MSE is going to be this thing called. Okay, let me explain all these big names. Number one, at the end is likelihood. Tell me, what is that? Something related with probabilities. Probabilities, can you help me to understand the difference between probability and likelihood? Any idea? Let's talk about your grades again. What is the probability for you to pass this class? Any class? Is this an example? Oh, that is an optimistic. Okay, let's say it this way. Theoretically, we do not use probabilities for your classes, right? And the reason because we do not use probabilities for the classes is because the angle could be 50-50. I do not want to use the example of the coin, but for you to pass the class, the probability is 50-50. Probability. Why? Because you have the same chance or the same opportunity to pass or fail, again, theoretically. That is the probability. However, can you agree with me that that is a very bad measure? Because in the real world, it is not true that she has this probability of 50-50, or he had the probability of 50-50, or someone there have the probability of 50-50. That is true as a probability. However, for this particular problem, talking about you passing the class or not, can you agree that there are some previous data that we need to consider? Because it's not really 50-50. The real problem is, tell me, you are a good student or not? Or tell me, what is your grade in the prerequisite class? Or in your other classes? Or your GPA? When you talk about probabilities, it's used like the coin. No previous data. Just tell me, probability, 50-50. You start with something. When you think about, okay, what is the probability, but considering previous data or previous situations, then we are talking about likelihood. The correct question here is, what is the likelihood for you to pass this class? Having that your GPA is something, what is the likelihood for you to get a pass or fail in the class? That makes more sense, right? I am talking about, for you computer scientists, a function that has two parameters This is my input, and this is the expected output. What is the likelihood? Knowing that your GPA is 4.0 for you to have the expected output and A in this class. Clear? Okay, there is obviously one way to calculate that, to calculate one probability having information. And the point is, the likelihood is what is the probability of having observed data, and that observed data produce something that we're expecting. In your case, for the neural net, what we have is our W's, the current values for the W's, and what we want is the expected value for the Y's. Make sense? Now, remember, we're going to use this to replace our error function, right? Instead of calculating the MSE, instead of calculating this difference between the output and the input, what we're going to do is to calculate the likelihood having this value that we calculate with the softmax and the W's of getting the output. Okay. Did you remember something that we're going to do with the error function in the backpropagation? What do we do with the error function in the backpropagation? What? The partial derivative? Derivatives. Okay. If you remember derivatives, how easy or how hard is to do the derivative of a function that have a logarithm? What is easy? The derivative of a function with or without the logarithm? For the derivative, with the logarithm. One of the easy things that happen when you do partial derivatives or derivatives is when you have a logarithm, there is something that happens between multiplications and additions. And there is some magic that happens that the equation becomes small. We need likelihood, right? But we're going to need to do the derivative of the likelihood equation. We are going to add to the likelihood equation the logarithm used because the logarithm is easy to derive. Really? Negative log likelihood. I explain the likelihood. I explain the log. Negative. Professor, why we make it negative? Remember that we're using values between -1 and 1. Moreover, remember that those values between -1 and 1 in the middle layer become values between 0 and 1. Remember this. Okay, we have values between 0 and 1. You know what is going to happen? That when we work with the likelihood, we're working with these values between 0 and 1. What is the logarithm of values between 0 and 1? Logarithm of 0, logarithm of 1. And suddenly you're going to notice that, okay, we need the logarithm to facilitate the equation, to facilitate the derivative. But the problem that we're going to have is that the logarithms are going to give us values between -infinite and 0. We do not want negative values. We're working with positive values. What do we do? You apply the minus. Negative log likelihood. Okay, it's a likelihood And you apply the log to facilitate the equation, and then you apply the negative because you want positive numbers. Well, you want, instead of minus infinite, you want infinite and 0. Tell me, what is the best value for negative log likelihood? Which is the value that you want to get? The perfect value. 0 or infinite? Why 0? Because it's your error function, right? And the value for the error function, the perfect value, is 0, because the y that you are looking for and the y that you have, identical. Negative log likelihood is going to give you a value between infinity and 0 is a good one. You can use that one as your error function. Okay, wait. Do I need to do the derivative of the likelihood? Then I need to research in statistics about what is the equation for the likelihood and so on. No, you only need to remember the name because you are going to use that name in your model, and the library already has the function that calculates this. Again, negative log likelihood is working with probabilities. You need to use an activation function in the output layer that also works with probabilities. Softmax and negative log likelihood, they are friends because they both work in that level. They are the only ones. No, they are not the only ones. But they both work in that environment. They can work together. Clear? SAS. Okay, so negative likelihood for the error, softmax for the activation in the output, linear for the activation in the middle, and initialized values, random, but not so random. And that is what we have here. We compile and run, and this is going to be your result. There are a lot of numbers, but help me, good or what? Point 0.65, almost in everything, 6.1, and this crazy confusion method. Still bad. Did we improve? We improve a lot. I mean, we were in 0. At least now we are in 0.6. Professor, again, is bad. Yeah, but you notice what happened when you change the initialization and what happened when you change the activation function. It's improved almost 50%. Good? We're going to improve this. Yes, of course, we're going to improve this. But one step. Done? Clear? Okay, still bad. Second version, another one. Model number 3. What can we do? You did a neural network from scratch. And you know all the elements involved in the neural network. The W's. We already improved the values for the W's, the initialization. The error function. We already changed the error function. The activation function. We already improved the activation function. What else can we do? One option, the layers. However, Professor, you just mentioned that one layer is going to be almost a solution error. We're going to add more layers, don't worry. But I can tell you right now, it's not going to make a big difference. Something else? The what? The what?
The learning rate.
The learning. That is going to be something that we're going to change. The learning. The learning. Remember what you did with the learning? Do you remember where in the full equation of the problem the learning is involved? Did you remember that what you are doing is this idea of calculate a new value for the W, and you use the previous value, and then you add or remove whatever the value for the derivative of the error function. But here we have this thing that is a constant that is going to change the learning rate. Do you remember this idea? This is the core idea of what is happening inside, right? Okay, there are two things that we can change there. And those two things are in the picture. Number one, something needs to happen there. And something could happen here. This is the core of the neural net. This is how we're calculating the change in the values. Good. Soft match, negative log likelihood, linear, Xavier, same input layers. Did we notice what is at the top with the blue box? A new element, right? Updated. The update. This is what we call the update. This particular step in the back propagation, the calculation of the next W value. What are we going to do to calculate the next W value? The default, the one that we have there, the partial derivative with this number constant, that is the learning rate. Use a simple multiplication between the constant and the partial derivative, right? Can we do something different? Yes. And there are several options to do that thing different. I am going to show you one, and you can change this with one parameter. One parameter, the new parameter, you can tell the library what is the updated, the equation that you want to use for that calculation of the next W's. If you put nothing, the default is what we have there. Partial derivative, the gradient, multiplied by a learning rate. But you can put different things. I am going to show you examples. Different things. Okay, like what? I just want you to keep in mind this equation, and I put here more clear. This is the equation that we're talking right now. This is what we talk when we mention this updated. This is what we have done. This is what we implemented. This is what we are going to change. Because this one is the equation that is moving this dot, this value of the W to the correct point, the point that the model is going to be using later. We're doing this for each of the W's. This, the original one. Options. For your reference, the first one represent this. The new value for W next iteration is the old value plus minus this constant, the learning rate for the derivative, the gradient, the triangle inverted. That is what we are doing. The default, the one that you program. One idea. You are calculating a position for a dog that is moving to a new position, right? Physics. Can we agree that a point that is moving if you're calculating new values for W, can you agree that you can calculate the speed of that W? How fast that W is changing? How fast it's moving from one point to another? Professor, but it's not a particle, it's just a value. Yeah, but you have someone with the knowledge of physics and it's like, okay, if I consider this W being a particle, and if I consider the changes of the values as a movement, that guy have a velocity. What happens if he's moving fast, or what happens if he's moving slowly? We can do something about it, right? Moreover, what if you multiply velocity for the mass of the particle? I am talking like in physics. Wait. These particles do not have a mass. What if you consider the value the mass? What if you use a constant then? Okay, I can calculate the momentum for the W. Again, it's not a particle, but I can apply that knowledge, right? And if I apply that knowledge, what you are telling me is that you can calculate the velocity and that you can have this constant, the mass. And then, what if we put this new number in the equation? And the next value for W is going to be the W as before, and it's going to be the learning rate with the partial derivative as before. But now we move this new element, velocity and momentum coefficient. Obviously, velocity is going to be calculated using this and the previous values. For calculating velocity, you need a group of values, right? So this new element here is not just a constant. It's a constant with this number, the velocity, that is kind of the summary of previous things that can happen with this W. Make sense? And just like that, with a physics concept, we have improved our previous equation. Really. I mean, the only thing that you are doing is an addition of this number, and that is going to change and improve the calculation of the learning for the neural net. Believe me, yes. Really? An addition? The point is not the addition, it's the background of why that addition. Wait. Is not enough. What if instead of calculating the partial derivative of the equation that we have, this error function of the W's, etc., did you notice the same error function? What if instead of just using here the velocity and the momentum constant, we calculate the partial derivative, not only, but we added momentum and the velocity here also inside of the calculation of the derivative, inside of the calculation of the change in the value. Did you notice this guy is still here, but now he's on here. Who is doing this? People in computer science, don't worry. 3 equations. Now we have the one that I introduced to you before and 2 more. Good. This guy is going to have a fancy name. this guy is going to have a fancy name. You can use the original one, you can use this one, you can use this one, and if you continue reading, there are more. And they are called updaters. Good? Okay, now I can go back to my example, the source code that I add. Updater, what I am passing as a parameter? An object. What is the type of the object? That is the name of the last equation that I showed you. And there is a class with that name. Yes, that class implements that equation. And I am going to pass as a parameter to my neural net. And with that, I am telling my neural net, hey, for your calculations in the backpropagation, use this guy. Call this guy to calculate the next values of the doublets. How many parameters I am passing to that object? Tell me, what is the meaning of those two parameters? Almost. Which one?
The velocity and the momentum.
The momentum constant, yes. The velocity is something that you need to calculate because it's not a constant, right? So momentum constant, yes. And what is the other?
Learning rate.
Because remember in the equation, learning rate was still there. Learning rate, momentum. Two values. Did you notice that? Well, I am not showing you the code here. You are going to notice in the full code, there is no more set learning rate because now here, the learning rate is there. Did I change something compared with the previous one? This is identical to my model 2, but with new updater, right? And my new updater is just this change in the equation. Clear? What is going to happen with the results? Do you remember what was the result before? 0.7. New results. Better? Are you telling me that we jump from 0 to 0.6? So half of the way, used with new initializations of W and used with new error function and activation function. That was kind of 50% of the path. And now we jump from 0.7, 0.6 to 0.9. Just because we consider this momentum thing in the calculation of the W's. Yep. Something that you're going to notice when you run this program, I am going to ask you to do that later. When you run this one, is slow than the previous one. You are going to notice that your laptop is going to take a little bit more time in doing the 10,000 iterations, because obviously these equations are a little bit more complex, need a little bit more time than the previous one. It's going to make sense, right? Okay, but the next question is, this is good? Happy we finished? No? What is the value, the threshold that we're looking for? 0.05. So that is kind of 0.95. Very close, still bad. I mean, we're better than the guessing thing. 0, 0.6, 0.91. We prove it is still bad. Okay, it is still bad. What can we do? Did you notice that the confusion metric is becoming better? Now I can see the main diagonal. Finally. That is going to happen with 0.9 and above, but still, it is bad. Now, model number 4. You know what happened? We are going to have different tools. And some tools are more powerful than the others. Right now with the data, we have this one that is the default one, that what they want to give us, the 0.6. And then we move. And if you notice, I give you 3 equations. And we go to the last one. They want to consider the speed, the momentum, and do the momentum inside and outside of the gradient. We say, like, let's use the most powerful tool. And when we get with the most powerful tool, the most complex equation is something that is 0.91, which is still valid. Okay. There is nothing else that we can change. So my only change, the important one, the one that you need to try. Did you notice the data? I am not going to use the last one, the super powerful one. I am going to move to the one in the middle, to the one that consider momentum, to the one that consider the learning rate, without adding that element inside of the derivative. Moreover, I am going to use this one in the middle that is not going to ask you for what is the value that you want to use, but for one that is going to use one value that is in the library inside that someone else take care of that. I am going to use a tool that is less powerful and is going to remove from me some responsibilities. And by the way, also, and this is used for you to play, I am adding another layer. Something that I am going to ask you to do later is, what if you move the data in the previous version without the 2 layers? You're going to notice that the 2 layers help, but they help 0.0001 for you to notice. But just to finish my example, it's like, okay, let's do a new data that is easier than the previous one. And also let's do 2 layers. Used to play with the layers. Did you notice what I am doing with the layers? How many layers and how many nodes in each layer? Do you remember that in the previous one idea was to have 1,000 here? I put 794 or something like that, just playing. But the idea is one number that is smaller than twice the inputs. So I was in that range. And the only thing that I am doing here is like, okay, if I have one layer with 1,000, let's create 2 half and half. Again, you're going to notice it's not relevant, but with that I can finish one model, 2 layers. Did you notice the connections? Inputs. I still have the same number of inputs. Outputs, first layer, are the inputs for the next one. Both are dense layers. This one, the outputs, are the inputs for the output layer, and finish with 10. These numbers, as you remember, use 3 general ideas of what they can be. Something that I am doing, I put on Canvas 2 papers. It is not mandatory for you to read it, but the papers talk about the architecture of neural networks. And the architecture means how many layers and how many nodes are recommended. It's a research paper, so you are not going to find a recipe there of how to calculate those numbers. It's just, you are going to get an idea of how broad is this. Now, with this one, again, just to play, the new data. Did you notice something missing here and here in the layers? I have 2 layers. What is the activation function of those layers? Did you notice that now that I have more layers, something that you can do is to move this activation function outside of the layers? It is not mandatory. You can put that guy here and here. What I am telling you is use what happens when you create global variables. If you put a value to the global variable and you do not put a local, that global is the one that is going to be used. For these 2 layers, without a specific activation function, I am going to use the one that I put above. And for the initialization of the W's in these two layers, I am going to use the one that I put above. For the last one, this output layer, this one is asking for a different activation function. Something that we did before. This one, the output is going to use this one instead of the global. The only reason to put the global is, to make your source code smaller. But if you prefer to repeat things, go ahead. It's more clear to read kind of the specification of each layer. When we are starting, that could be something that we want to do, but not needed. Good? Okay. Did you notice the name for the data? Do we know what is that? Let's see. Number one, something that we introduced before was the momentum. With the momentum, we put a fancy name to that. The nested of momentum. Yeah, nested of is the last name of the guy. Another thing that we can do in the middle is this thing. Adaptive estimation of the movement. Remember that the momentum was connected with the speed and the movement of the value to the correct position. Momentum is just one way to measure that thing. There is this idea, adaptive moment estimation, and the name summary. That is all about the learning rate. Do you remember that the learning rate still was a constant? The number that is multiplying here. What if instead of this constant here, what we do is to use a different value for the learning rate for different W's? Or the same thing that we did for the initialization of the W's. Instead of a constant initialization, random value. Or here, learning rate, instead of one value, different values, not random, use different. What we do? Easy. You start with one value, but then you adapt the value. And what does it mean to adapt the value? Use smooth the value. How? Instead of using the new value, what if you do an average of the new value and previous values? What if you have the learning rate, but then you update the learning rate somehow, and you have the previous one, you have the one that you paid, and then you combine these two, smooth thing, and the combination of these two is the new one, but then this new one is going to work or not, but this one take into consideration the other two, and you smooth this one and this one. Yes, guys, I am oversimplifying the idea. But this idea of learning rate not being constant, but change, adapt, considering previous values, that is the key idea of something called the adaptive model. Okay, so we have the add-on for a learning rate that is going to change. And then we have this other that use the momentum, that is the nested of thing. So can we put these two together? Can we use the momentum, like in our equation before, the velocity and the constant? And can we also update the learning rate instead of the number that we pass in the nested of, make that learning rate to be adaptive? Why not? It's just the equation is going to be more complex. Take the equation for nested of moment and put together with the equation of blip. And can you get the name? Yeah, that is what we change in the model. This, with the adaptation with this guy, the constant now is not a constant. And the only thing that I need to do to take access to all that mathematical improvement of the equation is I would like to have an updater, and the updater is going to be n Adam. Professor, should not be everything uppercase? No, because remember, here is Java. In Java, only the first letter is uppercase, so the n is uppercase, and everything else lowercase doesn't matter, but they are all uppercase in the book because it's initials of some name. Tell me, can we use this adaptive new method without the momentum? Can we use the equation with the learning rate adaptive and forget the momentum? By any chance? Because this guy, the n Adam, is momentum plus learning rate adaptive, right? We can use the both together before we use the momentum without the adaptive learning rate. Can we use the adaptive learning rate without the momentum? What could be the name for that? And what is going to be the name of the class? Uppercase. You have a class nested up, you have a class Adam, and you have a class Nadam. And if you understand what is the concept, use the explanation that I provide, oversimplify it. Good. Which one is the better one? The most complex. Next, the other? The addition, right? If you remember that, you can play with them. If you want to go to the details and check the equations and improve those equations and create your own data, different way. Okay, what do you think is going to happen with this guy? That the only improvement, the one important is Nadam instead of nested up. I really hope it's good because we're not off of time. Good enough? 0.05 was my goal. 0.05. I am done. I finished with you. Good. Do we understand the difference between the four models? All these new concepts that I introduced. Why this is better than the previous ones? Hopefully, yes. And if so, we did it for the week. Homework, guys. Two things. Number one, you are going to have, if I remember correctly, I am going to post an announcement, but I think you're going to have a quiz for this week. So you're going to have a quiz that opened today and closed before our next lecture. So I hope I send a reminder, but it's going to be a quiz with 10 questions and basically with concept questions. So far, I think we have covered a lot of concepts. So I just want to be sure that you are kind of getting the idea with the concept. Remember, it's a quiz, 10 questions, half an hour. You can have your notes open. My recommendation, first review the material, then go for the quiz. You are not going to have enough time to just search for every single answer. The quiz, simple questions. Obviously, do not include Adam and those crazy things. Are concepts, the basic ones, previous weeks. That is your homework. Other than that, my request for you, review the source code from this class and the previous one, because next week, I want to ask you to program a model for some inputs, and we need to talk about it. Good? See you next week. Thank you.